In this video, we will be showing you how to demonstrate the relationship between radius and angular acceleration with a quick lab using simple objects and the Firefox application. What you will need for this lab is toothed gears/sprockets of varying sizes, a smooth flat ramp of a known angle, and a phone with the Firefox application installed. Remember, if the gears are too thin and don't stand up at their own, try to attach a rod and connect 2 or more gears together so that they are less sensitive and won't fall over. Now it's time for the lab. Position the ramp on a flat surface and use Firefox to take its angle. Next, take one of your sprockets and hold it at a marked distance near the top. Put the phone with Firefox open with the audio scope tab next to the ramp. Now set this recording duration to at least 300 to 500 milliseconds so you have more data to work with. If you wish, you can connect the Firefox app to a computer using the remote access feature to export the data easier. Roll the gear/sprockets down one by one, recording and exporting the data after each trial. Make sure to repeat each trial at least a couple of times so you have more accurate data and less error. Now you have all this data, you have to turn it into actual results. But how do you do that? Well, I'm going to show you. Our goal is to find the angular acceleration of the sprocket rolling down the ramp. We first start with the period. In order to find the period, the peaks of the recorded wave are marked down and the differences between the 2 consecutive peaks are measured. Alternatively, the troughs can also be measured, and it won't make much of a difference. Here, both peak and trough measurements are listed to the nearest hundredth of a millisecond from the inversely proportional relationship. F equals 1 over t. Frequency is 1 over period. The frequency over each time period can be found, since t, or the period, is in milliseconds. It is important to convert that into seconds before inversion. Now, since the angular velocity is directly proportional to the frequency of clicks and inversely proportional to the number of teeth in the sprocket, as shown by the equation, omega equals 2 pi times f over n, or that the angular velocity equals 2 pi times the frequency over the number of teeth. This can be automated for each calculation frequency. Finally, to find the angular acceleration, take the data of the angular velocity and find the change of that over time. Although you now know how to use your data, you still don't know how we got to this point. To solve this, Leo is here to explain how we derive these formulas that you just used from torque, moment of inertia, and angular acceleration.
So we know that the torque is equal to the moment of inertia times the angular acceleration. Therefore, rearranging the terms a bit, angular acceleration equals torque over the moment of inertia. We know that torque equals force times the radius, and that force comes from the friction of the ramp on the sprocket rolling at a distance of r, the radius of the sprocket. And if we assume that the sprocket has the same moment of inertia as a disk, therefore the moment of inertia of this sprocket will be approximately equal to 1/2 mr squared. Canceling the r terms, we have 2 mg times sine of theta, theta being the slope of the ramp, times mu, the static coefficient of friction for the ramp on the sprocket, over mr. The mass cancels out. This leaves us with angular acceleration equals 2 times g times sine of theta times mu over r. From this, we can say that as a hypothesis that angular acceleration will be inversely proportional to radius. In order to measure the angular acceleration, we can first count from the trials the periods from each peak to peak and trough to trough. So in order to find the angular acceleration, we can first find the angular velocity and finding the change of that over time. In order to find the angular velocity at any particular point, we first find the period at that point, find the frequency using the relationship period is 1 over frequency, counting the number of teeth on that sprocket, and using the equation here, angular acceleration equals 2 pi times the frequency over the number of teeth on that sprocket to find the approximate instantaneous angular velocity at that time.
Once you have compiled all your data, you should get your results, and they should look a little something like this. In this graph, we graphed radius in relation to 1 over angular acceleration, and you can see that as the radius of the gear increases, 1 over angular acceleration does as well, meaning the angular acceleration itself decreases. However, in our graph, you can see that the error bars are very large. This could be from a number of reasons: inconsistent testing conditions, tilted surfaces, or changes in friction. But if this happens in your data, you can always try again. And with that, thank you for watching, and we hope that you come back for more science.